All right, ever stop and wonder how on earth developers build these massive, super complex apps and websites we use every single day without them just, falling apart? Well, the answer is this really powerful philosophy called Object-Oriented Programming, or OOP for short. And today, we're going to pull back the curtain on the invisible architecture that pretty much runs our entire digital world. Let's get into it. So, let's kick things off with a pretty huge question. Imagine you had to build a complex digital world completely from scratch. I'm talking a massive online game or a global banking system. Where would you even begin?
And maybe more importantly, how would you do it without the whole thing turning into a tangled, unmanageable mess? Because that's the real challenge here. Modern software is incredibly complex, and taming that complexity, well, that's the name of the game.
So before we jump into the solution, we really need to understand the problem. What are programmers actually trying to do when they build these enormous systems? Turns out there are a few goals that are pretty much universal.
According to our source material, it really just boils down to these three things. First, robustness, right? The software has to work correctly and not just totally crash when something weird happens. Second, adaptability. It has to be able to change and evolve over time. And third, reusability. This one's huge. You should be able to take bits and pieces and use them again so you're not starting from scratch every single time. And the stakes here, they can be incredibly high. We're not just talking about your favorite app crashing. In some systems, a lack of robustness can be catastrophic. The source actually points to the Therac 25 radiation therapy machine accidents back in the 80s, where simple software bugs led to patients getting massive overdoses of radiation. So yeah, getting the design right is absolutely crucial. Okay, so how do we hit those goals? Well, this brings us to object-oriented programming. And you got to understand, it's more than just a way to code. It's a whole new philosophy for organizing software. The big idea here is to model your software after the real world, which, let's face it, is made of objects.
So what is an object anyway? Well, at its core, it's just a self-contained little component. Think about it. A car is an object, but it's also made of other objects. You've got an engine object, right? It has properties like horsepower and cylinders. That's what it is. And it has functions like start and accelerate. That's what it can do. OOP is all about building software from these smart, self-contained little actors.
Now, this whole philosophy is held up by three foundational principles. You can think of them as the pillars. These are the core rules that let developers manage all that chaos we talked about and build software that's robust, adaptable, and reusable.
The first pillar is modularity. Think about it this way. You wouldn't build a house by just throwing all the plumbing, electrical wires, and wood into one giant pile, right? No, you build separate systems that all work together. Modularity is the exact same concept, but for software. You break a giant problem down into smaller, independent, and much more understandable modules.
The source material uses this diagram to show different parts of a system. But a perfect example is just the apps on your phone. Each app is its own little module. Your calculator app doesn't know or care how your weather app works. They're independent. That's modularity, and it's what makes them way easier to build, test, and update. Pillar number 2 is abstraction. And this is really the art of hiding complexity. When you drive a car, you've got a steering wheel, an accelerator, and a brake. That's it. You don't need to know anything about internal combustion or the physics of hydraulic braking systems. Abstraction gives you a simple interface to a really complex system. A really great way to think about abstraction is like a blueprint for a house. The blueprint shows you where the rooms are and what they're for, but it hides all the messy details of every single wire and every pipe. It gives you the what, not the how. And that right there is the essence of abstraction. And our third pillar, encapsulation. This one is all about protection. It's the idea of bundling an object's data and all its functions together into a single, sealed-off unit. Why? To prevent other parts of the program from accidentally reaching in and messing with its internal workings. Think of it like the plastic case on a computer. If modularity is deciding the computer needs a separate power supply and a motherboard, encapsulation is putting a protective case around each of those parts. It protects their delicate internal wiring from getting messed with and just gives you a few simple ports to plug into. That's exactly what encapsulation does for our software objects. Okay, so we've got these big philosophical ideas: modularity, abstraction, encapsulation. But how do we actually, do it? How do we create these objects in our code? This is where we get into the nuts and bolts.
The whole process kicks off with something called a class. Now, a class isn't the object itself, not yet. It's the template, the blueprint that defines what an object will be and what it can do. It's basically the architectural plan for the house. Let's look at a concrete example from our source material. Take a look at this code here. It defines a credit card class. See how it has a place for a customer, a bank, an account number, a balance? This is the blueprint. It doesn't represent any single specific card yet. It just defines the structure for all credit cards we might want to create later on.
So if the class is the blueprint, then the object, well, that's the actual house you build from it. In programming, we call this an instance. You can use that one credit card class, that single blueprint, to create thousands of unique credit card objects, each with its own customer, its own balance, the whole shebang.
And now for what might just be the most powerful concept in all of OOP: inheritance. This is where that goal of reusability we talked about really comes to life. It's a way to create new classes based on existing ones. It's like the ultimate copy and paste shortcut. Looking at our source, we can see exactly how this works. This diagram shows a new class called predatory credit card that inherits from our original credit card class. What does that mean? It means it automatically gets all the features of a normal credit card, but then we can add our own new specialized features right on top. Just look at how efficient this is. The new predatory credit card doesn't have to redefine what a customer is, or a bank, or a balance. No, it gets all of that for free. It just adds one new piece of information, the annual percentage rate, or APR, and it tweaks the behavior of how charges are processed. That's it. And the magic that makes this all happen in the code? It's often just a single line. Right here, on line 15, you see that super function being called. This is the new specialized blueprint telling the system, hey, go run the original credit card setup first, and then I'll just add my new stuff at the end. This is reusability in action, right here. So why does all this matter? I mean, this isn't just some clever programming trick. It has massive real-world benefits. You build software way faster because you're not constantly reinventing the wheel. It's way easier to maintain. Fix a bug in the main credit card class, and boom, all the specialized cards that inherit from it are fixed too. And it just helps you organize your code in a way that logically mirrors the real world.
So, to wrap things up, I'm going to leave you with a question to chew on. Now that you're starting to think in objects, how would you begin to design the software for something as insanely complex as a self-driving car? What would your main objects be? A wheel object? A GPS sensor? Maybe a braking system? This way of thinking, it's the very first step to taming complexity and building the future of technology. Thanks for tuning in.